Hello, dear viewers. Welcome to my tutorial video. In this session, I am going to show you how you can create a PID program for Siemens S7-1200 series PLC, and using this PID program, you can control temperature of a process for air heating system. In this video, you will go through the process of interfacing control elements with the S7-1200 PLC, configuring PLC input-output channels with respect to these control elements, as well as creating PID control program using TIA Portal software, and finally perform a real-time temperature control of the air heating system using this PID control program. To understand the PID control operation, we need a real-time temperature process assembly, which will be controlled by the PID program of PLC. For this purpose, a small thermal chamber has been developed on experimental basis for implementing PID control operation by PLC. This will give you a clear idea about PID control mechanism with a real-time process operation. The real-time process assembly consists of a thermal chamber, inside which an air heating element and an air circulating fan have been placed. During process operation, the fan inside the chamber spins continuously at constant speed and circulates the ambient air throughout the chamber at constant flow by pulling the ambient air into the thermal chamber through inlet duct and forces out this air from the chamber through outlet duct. During passing of air through the chamber, the air is passed over a PTC heater and the air gets hot. Thus, the circulating air achieves higher temperature while passes out through the outlet duct of thermal chamber. Our desired operation is to heat up the air to user-defined target temperature by regulating heater power. The PID control program of PLC continuously adjusts or regulates the heater power to maintain the chamber outlet air at desired and stable temperature. Now take a look at how we can proceed to implement PID for this process assembly of thermal chamber. For maintaining chamber outlet air temperature to the target value, first measure the temperature of chamber outlet air and get a signal to provide to the PLC input. Depending on the existing temperature measurement and requirement of outlet air temperature, the PLC makes analog output signal to regulate heater power. To drive the heater using PLC analog output signal, we can use analog signal to PWM power converter, which receives the PLC output signal as input and provides a PWM power output to heater. Thus, based on the PLC analog output signal, PWM power converter continuously adjusts the heater power to achieve the required temperature of outlet air.
The temperature measurement is done by using the PT100 temperature sensor and a temperature transmitter. The PT100 sensor directly senses the temperature of outlet air and changes its resistance, which is then converted to 0 to 10 volt DC signal by the transmitter. Here, the transmitter has the temperature measuring range from 0 to 100 degrees centigrade. So, depending on this measuring range, the temperature transmitter gives output signal from 0 to 10 volt DC, which is then provided to PLC analog input. To monitor the chamber inlet and outlet temperature locally, one temperature meter has been placed in the inlet path and another temperature meter has been placed in the outlet path of thermal chamber. Now move to the PLC analog output and controlling elements to regulate the heater power. The S7-1200 PLC analog output provides output signal from 0 to 20 milliamps, which is converted to 0 to 5 volt DC signal using 250 ohm resistor. The 0 to 5 volt DC signal is then sent to input a voltage to PWM power converter, which provides power output to the heater in the form of pulse width modulation. Thus, depending on the value of voltage input, the converter adjusts the duty cycle of its output power, which will determine the percentage of maximum power that will be provided to the heater. Thus, the heater power is continuously adjusted by PLC output signal until the outlet air temperature reaches to required value. Now, before to proceed for PLC programming, let's have a look at the PID algorithm and its associated parameters, depending on which PLC makes output. The PLC reads the existing temperature of outlet air by the analog signal received from the temperature transmitter. The existing temperature read by the PLC is called process value. For temperature controlling using the PID program, the user has to set the target temperature in the PID program, which is often called set value. The PID program continuously compares the process value with the set value and makes an output signal which will adjust the heater power to maintain the outlet air temperature to target value. The output of PID is called manipulated value. The PLC provides output in the form of electronic signal 0 to 20 milliamps, but during process operation, we monitor this PLC output in the form of percentage value, considering total range from 0 to 100%. Considering the difference between SV and PV as error, the manipulated value, or PLC output, can be found from the following algorithm shown in the video. If we look at the PID algorithm, we will find that there are three parameters: proportional constant, Kp, integral constant, Ki, and the derivative constant, Kd. For precise and stable temperature control, we have to set the proper values for these three constants during the PLC PID programming.
Now proceed to PLC program for PID control and analog input-output configuration of PLC hardware using the TIA Portal software. First, open the TIA Portal software and create a new project for Siemens S7-1200 CPU 1214 AC-DC relay. The project has been created for S7-1200 PLC, and we are now on the PLC device configuration window. The PLC selected for this project has no inbuilt analog output channel, so a signal board of one analog output channel has been plugged directly into the front of PLC main unit, so we need to configure it in the TIA Portal software. From the tree of hardware catalog, locate the specific signal board for analog output and drag it into the slot on the front of PLC mainboard. Now proceed to configure the analog input and output channel of PLC. This configuration will properly interface process temperature transmitter and PWM driver with the PLC. Navigate to Properties tab for PLC main board. Go to the tab for analog input and expand it. Click on the General tab. On the right side, you will get option for providing channel name and comments. Expand the next tab for analog input. Click on the channel number 0. On the right side, note that the signal range for this analog input channel is 0 to 10 volt DC, which is fixed and cannot be changed for this S7-1200 PLC. Move to click on the input-output address for the analog input channel. On the right side, you will get option for setting input address for PLC analog input. Keep this default address range for PLC analog input channels. Now go for Signal Board for analog output and expand this tab. Under the General tab, click on the menu for Catalog Information. This signal board provides only one channel for analog output, and this channel provides 0 to 20 milliamp current signals or 0 to 10 volt DC signal. Expand the tab for analog outputs and click on Menu for channel number 0. On the right side, set the type of signal as current.
Note that the signal range has been set to 0 to 20 milliamp when you set the type of signal as current. Move to Input-Output address for this analog output channel. Here, you have to set the memory address for analog output channel. Change the default address as 100. So in the PID program, we will use memory address for analog output as QW100. We have come to finish configuration for analog input-output of PLC hardware. In the next step, we can proceed to PLC programming for PID control.
For PID programming, at first we have to add cyclic interrupt organization block in the PLC program. Generally, PID program of Siemens PLC is implemented in cyclic interrupt organization block to ensure consistent sampling cycles. From the project tree, navigate to Program Block and click on the tab for Add New Block. From the list of program blocks, select the desired block type as Organization Block. A list of organization blocks has been appeared. Select the type of organization block as Cyclic Interrupt. On the right side of this window, default value for cycle time has been set 100 milliseconds. Keep this default value to set the cycle time for this cyclic interrupt block. On the top left of this window, navigate to Field for Block Name and provide a name for this block. Click on the OK button to add this cyclic interrupt block in the list of program blocks. We are now in the page for Cyclic Interrupt Organization Block, where we can proceed to create PID program for our desired process control. Go to Instruction menu for Technology Objects. Expand the menu for PID Control. Under the menu for Compact PID, drag and drop PID Compact block into the Cyclic Interrupt block. We have come to get the desired PID block. This PID block functions on the value of a number of operational and tuning parameters. To handle these PID parameters' value, we have to create a number of variables in a data block and put these variables in the field for these PID parameters. Under the menu for Program Block in the project tree, click on the menu for Add New Block. From the list of available program blocks, select the block type as Data Block. Go to the field for Block Name and provide a name for this data block. The Data Block Editor window has been opened. Here we have to create a number of variables that will be used within the PID program. Now start to define necessary variables with their associated data types and default values. All the necessary variables with their associated data types and default values have been created. Close this window and go back to the window for PID program block.
Now, configure the PID block with the variables that have been created in the data block. For executing of PID algorithm, the PID block get their parameters values from these variables. Navigate to field for PID parameter setValue and put the variable setValue, which has been created in the data block. Next, go to Input Parameter. Here you will find two types of input parameters. One is input and other is input PER. Use the input parameter when the input is scaled to process value range in engineering unit. To use this input, first we have to scale the PLC analog input to engineering value using ladder program and put the scaled value in the field of input parameter. For simplification, we will not use this type of input parameter. Instead of using input parameter, we will use input PER parameter. Here we will use raw or unscaled value, which is processed directly from the analog input module. So, in the field of input PER, put IW64, which is memory address of analog input channel number 0. In the next step, fill up the fields for other parameters with respective variables from the data blocks. We have come to finish mapping necessary parameters with the variables created in the data blocks. Look at the parameter for output PER. Here, the field for this parameter has been filled up with analog output address QW100, which have been configured to give analog output as 0 to 20 milliamps. Now, before to run this PID program, there have some basic settings that must be done for configuring this PID block properly. These PID configuration settings can be done using the PID commissioning tool. In the top right corner of this PID block, click on the icon for commissioning window. From this window, we have come to get these basic settings for PID configuration. Click on the first setting for controller type. As we are controlling temperature parameter, select the controller type as temperature and measurement unit as centigrade. In the bottom, set controller mode as automatic. This will turn the controller mode into automatic mode every time the PLC starts to run. Next, go to the configuration setting for input-output parameters. First, look at the option for input parameter. As it has been previously mentioned that the input for the PID has been set to input PER, in this input selection field, set the input type as input_PER_analog. Set the controller output type as output PER_analog. This setting will make the PID to provide output as a raw peripheral integer type value in the range from 0 to 27,648, which will map the PLC analog output module to create analog output signal in the range from 0 to 20 milliamps. Next, go to the setting for process value limit. Here we have to set the high limit and low limit of the process value range. In our temperature control process, the temperature is controlled between 0 to 100 degrees centigrade, and temperature transmitter has been calibrated as 0 to 100 degrees centigrade. So, when the PLC receives input from the transmitter, PLC input must be scaled from 0 to 100 degrees centigrade, which can be taken as process value range in this PID configuration setting. So, in the setting of process value limit, set the process value high limit as 100 and low limit as 0. Next, go to the tab for process value scaling. Depending on the previous setting on process value limit, process value scaling has been automatically set to 0 to 100 degrees centigrade. So keep this default range value for setting this configuration menu.
Finally, move to the last configuration settings, PID parameters. Here you will find options for setting the value for PID parameters. Setting the value for these PID parameters accurately will optimize the PID performance. Using the auto-tuning function, we have found the more accurate values for these parameters. So these default parameter values will be replaced by the updated values found from the auto-tuning function. In the option for tuning rule set, controller structure as PID. Now back to the window for PID program block. There is one more issue that should be taken in consideration when the controller switches between automatic and manual mode. When the controller switches from automatic to manual or manual to automatic mode, the controller output suddenly jumps from existing to other value, which can cause the process unstable. So to ensure smooth and uninterrupted controller output, separate ladder logic has been developed in the main organization window. So go for main organization block to view this ladder logic. Look at the ladder logic in the first network. When the controller runs in automatic mode, the move function in the ladder logic assigns the PID output value in auto mode to the controller parameter manual value. So when controller switches from automatic to manual mode, the controller parameter manual value will hold the last time controller output value in automatic mode. So there will be no fluctuation in the controller output value at the moment of switching controller mode from automatic to manual. Move to the ladder program in the second network. When controller runs in manual mode, the SV will track the process value, and this function is executed by the ladder logic of this second network. During switching of controller mode from manual to automatic, the controller parameter set value will hold the last time process value in controller manual mode. This will keep the set point near to the process value during switching to controller automatic mode, which will prevent sudden change in controller output as well as provide a stable and bump-less process operation. Now switch back to cyclic interrupt organization block for PID program. We have come to finish the PID program with its entire configuration. Now compile this PID program and PLC hardware configuration and download this to the PLC.
The PID program with PLC hardware configuration has been transferred to PLC, and we are ready to perform PID operation for real-time temperature control. Turn on the monitoring option to observe the status of running PID program and get the different tag values of PID block. For PID operation, first we have to activate the PID block, which is now disabled. Close the normally open contact of the memory address M0.0. Now the PID controller is activated and the controller is executing the PID algorithm in the automatic mode. Note that the set value or target value is set to 0 by default, and this is now lower than real-time temperature value shown in the process value tag of PID block. So the controller output has been set to 0, and the heater is now turned off. Now navigate to PID parameter set value and set a target value for this controller. Note that the controller has set its output to 100% and the heater is turned on. The chamber outlet temperature is rising now, that is visible in the controller parameter process value. The chamber outlet temperature is also visible from temperature meter located at the outlet path of the heating camber. Now continue to observe whether the chamber outlet air temperature reaches to target value that has been set in the PID parameter set value. Note that the process value or chamber outlet air temperature has reached to the controller set value and it is remaining in stable condition. Now change the target value and observe the process response. Note that the chamber outlet air temperature has started to increase. Again, the chamber outlet air temperature or process value nearly reached to the new set value. Now switch to manual mode using the controller parameter manual enable. Note that depending on the ladder logic in main organization block, controller retains its output value equal to last time controller output value in the moment of controller mode switching, from automatic to manual. Now take a look at controller parameter set value. Controller parameter set value is tracking the process value. Now again switch the controller mode into automatic mode. Note that the target value has been set equal to last time process value during controller mode switching, so there has been no sudden change in the outlet air temperature. Now go to the commissioning window and get the values for PID tuning parameters. You have to set these parameter values correctly for optimal control performance. These tuning parameter values have been found from the auto-tuning function of PID programming block, which was not shown in this video. In the next video, we will demonstrate how to tune the PID controller using the auto-tuning function of PID programming block.
The PID control program for air temperature control is properly functioning now. Now, put the sensor of inlet local temperature meter in the outlet path of the heating chamber. Check whether these two temperature meters show the same temperature value for outlet air, as both of these meters have been placed in the outlet path of the heating chamber.
We have reached almost at the end of this video. I think this video will be helpful for you to get an idea about how to implement the PID control for real process using Siemens S7-1200 PLC and TIA Portal software. If you find this video helpful for you, please like, share, and make comments on this video, and don't forget to subscribe this channel.